We're going to talk about something exciting we've been doing. Um, it's actually a joint project between CSIRO InterSystems and Austin Health, but we've sort of it's going into Austin in a couple of weeks for user testing, so we don't have them sort of marked off here. So far, it's been the two organizations sort of doing the work. I'd like to start by acknowledging the traditional owners of the people of the Kulin Nation here, where we are at, of the lands we are meeting on, and paying my respects to the elders past and present. And really, I'm going to grab that, and I'm going to move a little out here because I'm quite loud anyways. So we are CSIRO. We are Australia's National Science Agency, in case you didn't know that. And our research and our sort of impact pathway is built on collaboration. It's built on working together with partner organizations, and it's about delivering benefit to Australia and the world. Me specifically, I work for CSIRO's National Digital Health Research Program, which started off in 2003. We've got, it started off as a joint venture between Queensland Health, who's coming to do that, and CSIRO in Queensland. But we've now got presence across the country really. We've got a Victorian colleague, Rajiv, he's here if you're from Victoria and you want to have a chat. And we've sort of grown to about, it's now about 160, 170 scientists and engineers and students and postdocs. It's all about building the pathway for digital transformation of healthcare. And like I said before, our success is built on partnerships. This is a great slide which I don't need to sell to this room, right? Why is demand forecasting important for hospitals? I think this room probably understands it better than I do, but there is that need for using data-driven transformations to make healthcare more proactive management instead of reacting to problems. And we hear of all of the ED crowding and the ambulance stamping, turning over governments and things like that. So really we can improve that. That would be great. About 9-10 years ago, we built a solution called the patient admission prediction tool for Austin Health here in Victoria. And we've got Zoran here if you want any questions for him. And sort of we built that as a standalone solution, and they've had it since then. It's got the ability to give you an overview of how many patients to expect, broken down by shifts, different types of day, who's going to come in by ambulance, who's going to come in on the pediatric side, the ability to look at that broken down by different clinical specialty units, and to have a 14-day outlook forward saying who's going to come in, what is my workflow going to look like, with the view of trying to transform that to being proactive management. And they've been using it quite efficiently. Problem is, it sits as a standalone tool, it doesn't integrate with the rest of it, and as systems mature, that was starting to become a problem. So, and we've been talking with InterSystems for quite some time around the idea that you build these really nice solutions, you trial them in hospital, and then somebody else comes along and says, we love your solution, can we put it in? You've already built it, you've tried it, it works. So how quickly can I deploy it? Okay, yeah, sure, it costs you about $500,000. Take another 9 or 10 months. And so you pretty much, when you go from one side to another, you're sort of restarting that whole process, just because everything's so disconnected. And we wanted to work on building a standards-based approach to decision support, so that as we build some of these things, it integrates across, it talks to the other systems that are within that environment. And once you've built it, you have the ability to take it and deploy it to other sites fairly quickly. You want 80% of that to be modular and transferable, and there's only a little bit required to get it working on another site. So we said, hey, this is a fantastic opportunity. Got the 3 partners to come together. Austin's got a use case. InterSystems has the tech. Sarah's got the algorithm. Why don't we try and use this as a way, and for saying this is how it needs to be done. So we got the data out of Austin, and we started building a model. And the approach we took, so we kind of had data for which went over the COVID period also, just so that you are able to look at changes away from normal and business as usual both. And we developed the model in a way where you did it iteratively, which sort of emulated how the model would be used, because what's happening is every day you have new data coming in, and you're using that new data to retrain your model and predict for the future. So now, and then for the next day you get new data coming in. So we sort of replicated that approach where we were getting data and we were using data in the last year before that to forecast for the next day or the next day or the next day into that period. So it's very important to sort of build your model in a way that replicates the use case, and there's a lot of work we've done in that space, and that's been a big part of that statistical rigor that we introduced into the process. What we landed up with was a new prediction model called ADePT, the Advanced Demand Prediction Tool, and that's built on a statistical machine learning approach. I'll give you an example of this is if you are familiar with hospital flow and how patient admissions happen, you'd know that you see this sawtooth pattern weekly, where you have on the weekends the numbers dip, and you sort of see this pattern continuously. Now, breaking this pattern down, what these machine learning is all about pattern finding. What these methods do is find a pattern in your data and project that forward. If you look at this, you can obviously tell that there's the sawtooth pattern in here. But you need to look really hard, and a machine's good at doing that, to see that there's actually also a trend, a slight upward trend here, which this picks up. Right? So the machine learning process, especially the SARIMAX statistical method we use, breaks that signal down into what is obviously that weekly sawtooth pattern and the trend, and then it pulls apart. If it can build something that explains this pattern and this pattern, then it looks at what are the remaining fluctuations and what it needs to put in place to explain that. Right? So that's how the method works, and it accounts for all of those factors. And this often is your sort of public holidays and other abnormal, really bad heat wave days and things like that. Benefits over some of your more modern machine learning methods. It's easily interpretable and it can retrain itself. It's a time series based approach, and so it can retrain itself very quickly, and so the model keeps rebuilding itself every time it's run. What we built back in 2012, 2013 and implemented at Austin in 2015 was then published as the most effective model out there then. What we did in this instance with this partnership is we've actually improved on the accuracy that we could offer. So this is what the original method performance was, and the error stayed between 5 and 10%, 10% being the max. We've actually cut that down. So we now, in some instances for the inpatient side of things, you are actually halving the error and you can predict a lot better. For the ED presentations, it's quite similar, and a lot of that comes from the fact that that sawtooth pattern and those weekly things that you're getting, the traditional approach would often not get that, which is something you don't see in the EDs. So you have fairly similar performance there, but you halve the error when it comes to your inpatient side of things. And I promise this is going to be the last graph because I'm handing over to Juanito after this. But also again, with the stuff we do, I think it's very important for the people that are using this to understand why you're getting a performance. Now with the clinical stuff we offer explainability in a sense of this patient, we are predicting a high risk or something for these factors. But for these operational models, it's important to really break that down a bit. So looking at performance for ADePT and two other approaches, one your sort of average-based approach, which most of the dashboards use, and a random forest-based sort of machine learning approach. You see these patterns where your gray is the actual, and your black lines are your predicted. These blue shaded areas are your public holidays, and some of the approach you see in comparison here, on the public holidays, because these are variations, and I showed you how SARIMAX breaks down the pattern into 3 different things, it actually gets the public holidays a lot better than any other method does, especially moving averages. And the other thing is, you see that the peaks of these are much better aligned here compared to moving averages, or especially compared to a random forest model. Now, if you can figure out, those peaks are your busiest days. Those are the times which are your worst crisis times, and those are the ones that ADePT captures best. So while we say we are improving the performance by 4 or 5%, while that may not make a difference, it's actually making a difference on your busiest days and giving you performance when you need it the most. So that's what we sort of built. We presented this at the HIC conference, the actual algorithm. But the exciting part of it, I have said this very often, I think the math is the easiest and the dumbest part of the puzzle. So tell us about a little bit more of the exciting stuff about how we are building it in a way that it can be interoperable and scalable, making it sort of fit into the Austin ecosystem, but also make it rapidly deployable to other people is Juanito.
He's being very humble here because they actually won an award, and probably you saw that in the morning. They won an award, innovation award from the MIT for at our Ready conference earlier this year. So they are actually the clever people. So yes, so all of that now, how did we deploy that using RS4 Health? And you saw probably some of the challenges that they had being interoperable, scalable, integrate. So the machine learning model is a bunch of Python classes. So how do we integrate? And we thought, yeah, our platform is ideal for that, okay? How do we integrate that into the Austin ecosystem now? There's different options that we had, okay? So this is just summary of them. The first one was an embedded approach, as we call it, where actually we're bringing the ML close to the data and actually embedding it inside Iris and close to the tables, okay? It has pros and cons, okay? One of the cons is a low reusability for future projects because it's not really based on a standards approach. But in order to go fast, good fit for operational decision support, which was actually the use case for ADePT and demand forecasting. And I've put a note there. So currently, the embedded mode is what we currently chosen for the implementation at the Austin. But there's two other options that we also had thought, we haven't explored that yet, is to have a machine learning model really decoupled and probably available as a package, easier to manage its life cycle and isolate from the complexities of organizations and how we get the data. The challenge with that is how do you manage additional components that you get to that? And the standards-based approach using standards like HL7 FAR, very interesting, and probably it's a hybrid of both of that. However, it's a better fit for clinical decision support, as in you use FAR as a standard in order to query information about a patient, so whether it's attributes, demographics attributes, or observations, using FAR in order then to interrogate the machine learning model, predicting whatever it's predicting. So after evaluating that, we decided to go with the embedded approach. This is what we landed on in terms of what we actually built, and that's going to go into testing at the Austin. The data sources are actually coming from TrackCare and FirstNet. FirstNet is used in the emergency department. TrackCare is the patient administration system. So we're getting HL7 messages, and from these HL7 messages flowing into Iris, we're actually building what we call raw tables. So these raw tables, referred to here as ODS tables, are actually the source of data on which we build the aggregations that the machine learning model will use. So the machine learning model, as Sankalp said, these signals need to be from aggregations of this raw data coming from HL7 messages. And we build all that in Iris, the tooling to aggregate that. We do have, as part of the model, an initial training and evaluation that needs to happen. So looking at the historical 4 years data to train and evaluate the model, produce the model. So we build that in Iris and using a functionality called embedded Python, which is basically using as much as possible of the code that they've developed and bring that into Iris and reuse that. And then after we have the aggregations, we produce what is called fitted models. So the fitted models basically is actually the model that's giving the prediction. And there's different models based on different service, based on different shift. There's a daily one, there's an hourly one. All that is based on the model that they've built. And this one is, there's a daily job that runs to update and produce a new forecast. So the way the model works is every data it gets every day from admissions, discharges, it will retrain itself overnight and produce new predictions basically every day. And that's how it learns from that historical set of admission and prediction data. And we are actually storing the prediction into some tables in Iris here and using a tool called InterSystems reports in order to produce the dashboards. We do have the intention of building REST APIs to make these predictions available to other tools that exist within Austin Health. So we have a tool called the Tier 1 tool, which is the main tool used across the whole organization to get visibility of admissions and capacity of beds in all the services. But for now, we just have, we have the reports that we're going to put in the hands of a customer for user testing and evaluating how that prediction is going with them. So in terms of project, where we at the next step, so we have to deploy into the test environment, actually integrate with the test feeds. There's a plan to actually have some production data itself to have a better, closer prediction, and also do some parallel running, because with the current tool that they have, while we know there's a lot of improvement with the new model that they've developed, but we do want to compare how is it with the existing tool and the new tool, and then we'll prepare a migration of the data and cut over of the new tooling for them. So I have some screenshots next on how that looks like. So these are for the emergency department, so the prediction hourly for every hour of the day and daily as well. But here's where the interesting part is. You actually see the split of the presentations. So what sort of presentation, whether it came from ambulance, whether it came from pediatric, and also expected departures, which is a discharge. So the team at Austin actually use these predictions. Currently, they manually enter that into their tier 1 tool, but they actually use that as hey, this is what we predict is going to happen at the different shifts in order to plan for bed capacity and manage the forecast of demand on beds. We also have, as part of the algorithm, what is called a 14-day outlook. So they're able to see over the next fortnight what's the prediction looking like, and again split across different type of admission types, as it's called. Inpatient, we have the same graph as well, a bit different pattern. What we've done here, we've split it also into different services. So what is referred to as CSU there is the clinical services unit, and the algorithm is actually producing the prediction based on the clinical service of where we are expecting the inpatient admission. The model, using that historical data of where the admission is in service, is able to do that prediction across the services. We've also split it based on different types of admissions, and also we have a 14-day forecast for the inpatient as well. Okay. Last but not least, yes. So what we found out, so some of the learnings we found. So while we're doing all that, that project was really, as Sankalp described, a way of building a scalable solution that we are able to port to other organizations or different projects, can really reduce the time to implementation. So we do have ticked a fair bit of these boxes on interoperability, integration with data sources, flexibility. On the other side, there's other things that we need to build into the solution. So things, for example, with performance monitoring. So how we monitor the performance of the model over the time. We're looking at possibly using third-party tools for that, to bring into that system to make it really, production ready, I would say, and able to port to other solutions as well. So in conclusion, so these are some of the benefits. I think Sankalp did touch on that, but that's kind of the aim and what we're aiming to have with building the ADePT solution on RS4 Health, to be able to have a flexible and scalable solution that we can then bring to over different organizations and really reduce that time to implement these type of projects every time. As Sankalp says, it takes $500,000 and 9 to 10 months. Hopefully we can cut that to something a bit more reasonable for organizations. That's it for me.